So as I was saying at the end of the last video, this is the beginning of 5.3b, and this is a kind of a new class of problem that still use exponential modeling. So we have a cup of hot water that's placed in a room where the temperature of the room temperature, is constant at 69.55 degrees Fahrenheit. The following water temperature readings were taken. So we measure the temperature of the cup of hot water, and no surprise, it's cooling down. Find a model for the temperature T in degrees Fahrenheit as a function of elapsed time in minutes. So let's just be clear about what it is we're trying to find here. Ultimately, we want a function capital T of little t, which is a little confusing, and this is going to model water temp at time t in minutes. So at first glance, you might think, oh, well, I'll just type all this data into the stat editor and I'll do exponential regression and then I'll have my model, right? Well, I mean, for one thing, how do you know that this is actually exponential regression is the best fit here? And the other thing is, well, that wouldn't quite be accurate. So the thing that we're missing is this room temperature. So that actually has an effect on our model, and we need to incorporate that in some way. So this general class of problem relates to something called Newton's law of cooling. Newton's law of cooling. And yes, there is also a Newton's law of heating, which we will talk about as well. But Newton's law of cooling says, suppose an object is placed in a medium at a constant temperature A, so the medium would be like the room that you put the object in, and the temperature of the medium is lower than the initial temperature of the object. So we're putting a hot object in a cool room, okay? The object's temperature T will gradually decrease until it reaches the medium's temperature. So let's just read this sentence again. The object's temperature T will gradually decrease until it reaches the medium's temperature. That is sort of a obvious fact, right? If you put a cup of coffee in a cooled room and you wait long enough, eventually there's going to be the room and the object will approach the same temperature. So we're actually going to make the assumption that the room will be held at a temperature and the object will cool down to that temperature, which is a little bit of a we're fudging things just slightly, but that's basically the situation. Okay, so in regards to this, we have to define the second quantity called the positive temperature difference. And it is positive. So positive means not negative, okay? So remember that. The positive temperature difference between the medium and the object. And that is the thing that can be modeled by a decreasing exponential function. So what is this positive temperature difference? Well, just as it says, it is just the let me just write the formula down here. It's the object temp minus the room temp. That's all the PTD is. And this will be positive because the object is hotter than the room, and so for the difference will be a positive difference. If we flipped it and we did room minus object, this would be negative since we're talking about cooling, but we're not doing that. Okay, so so object minus room is positive. And this is the quantity that we're actually going to directly model with a decreasing exponential function. Okay. So the confusing thing about this is that we're not directly modeling the coffee temperature or the cup of water temperature. We are directly modeling the difference between the object and the room. Okay. And that's always a bit confusing. So in applying Newton's law of cooling, we find a positive temperature difference model. That's the thing that we actually do the regression for. Okay. And then we solve the above for the temperature model. And then we use the temperature model to make predictions. So there's basically like two steps to this. Step one is this. We get the regression model for PTD. And we'll go into all this in detail in just a moment. But then step two, that's number one. And then step two is we kind of convert the regression model for PTD, sorry about that noise, to a object temp model. Since the object temperature model is the thing that we actually want, we have to kind of do this conversion. And when I say convert, I mean just move some, basically we just solve this little equation for t. Okay. Now I know this is all kind of mysterious at the moment, so we need to look at an example where we actually do this. So let's do that. All right, so let's do this for our cup of water. Right? So here's our data, our initial data. And what we have to do, let me just sort of sketch this out on the whiteboard for you. What we've got to do is organize all this data and then basically add in a PTD column. So we've got our L1, which is our times. And that's 0, 10, whatever it was, etc. 0, 10, 20, 30, 40. And then there's a couple of ways you can go about this. I think what I tend to do here is I go ahead and I enter my L2 column, and that's going to be my object temperatures. But the thing about this is you've got to remember that we're not done yet. We can't do the regression yet. So I can put my object temps in. You know, that's the actual cup of water in this case. So 169.63 and so forth. Okay. But then we have to go to column L3, and this is going to be our, let me move this over a bit. Column L3 is going to be our actual minus, oops, I'm sorry, our PTD column, which is, in this case, this is going to be object minus the room. Now I've got, I need a little bit more room to write here. So what that actually looks like in terms of, you know, what do we type in, is we type in L2 minus our room temperature, I believe, is 69.55. Yeah, 69.55. So 69.55. So basically we're just subtracting 69.55 degrees from every one of these values and then putting that here. And then once you've done these three things, then we can do the regression. But remember that we are going to do regression not on L1 and L2, but on L1 and L3. Okay. Because we want to use this data for our regression data. So that's the first phase. That's basically like this step, step one. Okay, so let's do that. I'm going to go ahead and enter this data. Okay, so I went ahead and off camera entered this data into my stat editor. So L1 is 0, 10, 20, 30, 40 as promised, and L2 are my room or my object temperatures. And so now is kind of the new thing. Go to column L3, and column L3 is going to be L2 minus the room. So that's 69.55. Okay, and so that brings up this set of data. And now we're going to do exponential regression. But for the first time, we actually, I think this is the first time, we're going to change our L. It's not going to be L1 and L2. Oops, and I just did L2. Let me fix that. Sorry. L3. And then we still want to save this as Y1. Now, if you have the other model of calculator, you can just, where it's like a table of values, and you just type in L1, L3. Same difference, though. Okay, and so this is what we call our PTD function. So the PTD function is exponential 96.82 times 0.961 to the t. That's our PTD function. So if you see any questions and it's asking you to find like the SSE, make sure that you pay attention to what function it's asking you to find the SSE of. So if it says find the SSE of the PTD function, do that with this regression, and then you can go on and find the temperature function for the object. So you got to be careful to separate those two things, okay? All right, so there's our PTD. Now let's go to step 2. Solve the above for the temperature model T. So that's, oops. Let me copy this down. So PTD equals temperature of the object minus A for like ambient room temperature, or if you want to write it like this, oops, except maybe do it the right way. You can write object minus room. Just remember that we're going to have to turn this into like functions and letters in a moment. But the ultimate goal is that I want to have an object function, right? So I need to take this little equation and solve it for objects. So that means I need to add room to the other side, which means that we're going to have PTD plus room. So in terms of like what this actually means for our calculations, this is the function, this is the regression function, y1, right? This is y1. But now we're going to take to y1 and we're going to add to it 69.55, and that will be my actual cup of water temperature. So basically you're going to go to y1 and then add 69.55 to it. And that's why you have to be careful about when you're doing stuff like finding the SSE and things like that, because we're actually going to change y1 now. So we want to make sure that when we change y1 that we are keeping that in mind with whatever calculations we do. So our T of t function is, let me get rid of that. That was something else. So this is our PTD function. So what I want to do is kind of just add on to this plus 69.55. Okay. Now what we want to see if we graph this, because think about what we're actually graphing. We're graphing what we want to have is a function that models the object temperature over time. And over time, you've got your room, which is at 69.55 degrees, and then you started off with this cup of hot water, which is up here. We want to see it basically do this, which is approach 69.55, right? Because it's cooling down to the room temperature. So let's check and make sure that what I have entered here actually graphs something like my picture. Right now I've got my window. Let's go up to like, this is in minutes, right? So let's go up to like 2 hours. So let's go to 120 minutes. And then we'll do zoom fit with that just to see what this looks like. And I'm about to run out of time here, so I'm going to have to stop.